Welcome to Science to Sleep By, where we explore the mysteries of the cosmos in a way that soothes the mind and stirs the imagination. Tonight, we journey into one of the most fascinating questions in modern physics. Is the universe actually two-dimensional? For centuries, we have trusted our senses, believing that we live in a solid, three-dimensional world. But new discoveries in black holes, string theory, and quantum mechanics suggest that reality may not be what it seems. Could our entire universe be a hologram, a projection written on a distant surface and unfolding into the depths we see around us? In this speech, we will wander slowly and gently through this breathtaking idea, from the birth of the holographic principle to its philosophical implications, from the experiments that test its truth to the meaning it carries for our lives. So settle in, let the noise of the day fade, and allow the wonder of science to carry you toward rest. Together, let us imagine what it means to live in a universe that may be far more mysterious and far more beautiful than we ever believed. We're going to ask the question that might sound impossible at first. Is it possible that the universe is not three-dimensional at all, but in fact only two-dimensional? The idea of dimensions is one of the simplest yet most profound concepts in physics. When children first draw a line on paper, they are working in one dimension, a single stretch of distance that can go forward or backward, left or right. Add another direction, and suddenly that line becomes a square, a field, a plane, and we call that two dimensions. Add yet another, and the plane rises into space. Suddenly we have volume, we have shapes with depth, and we call that three dimensions. And then, if we listen closely to the whispers of modern physics, we hear something even stranger. The suggestion that our universe may not stop at 3. It might contain 4, or 5, or 10, or even 11 dimensions. But before we rush into those abstract spaces, let's pause and sit with the fact that the familiar 3 may not be as secure as we think. It could be that everything you see and touch, every galaxy and planet, every atom and cell, is actually projected from a deeper truth, one that requires only 2 dimensions. This may sound like science fiction, the kind of thought experiment that belongs in late-night conversations or futuristic novels. But it is not just fantasy. It comes from some of the most serious, rigorous work in modern physics. It begins with a simple but unsettling observation. When we measure the information contained within certain cosmic objects, like black holes, the math seems to suggest that the data is not stored in the full three-dimensional space of the object, but only on its surface, in 2 dimensions. Imagine that for a moment. Imagine if the vast interior of a star collapsing into a black hole, something that could once hold millions of Earths, is in some sense an illusion, and that all the information describing it is painted across its surface, like patterns of ink on paper. This is where the mystery begins, and it forces us to reconsider what we mean by reality itself. But before diving into black holes and holograms, it's helpful to step back and think about how humans have always perceived dimensions. For thousands of years, people lived without ever questioning the idea that the world around them was flat, that the earth itself was like a plane stretching outward. To them, the horizon seemed endless, and the idea of living on a sphere was almost impossible to imagine. Only with time, with exploration, with daring, did humans slowly accept that their flat plane was an illusion, and that they were in fact moving across the curved surface of a three-dimensional globe. If that great shift in perspective was possible, could it be that we are standing on the edge of another shift, one where our solid, spacious, three-dimensional universe is actually just a surface, a kind of cosmic canvas, and the depth we believe in is a trick of perspective? In the United States, where so much of modern science has blossomed in laboratories, universities, and observatories across the country, these questions are not abstract curiosities. They are at the heart of some of the most ambitious experiments and theories. From Princeton to Caltech, from Harvard to Fermilab, researchers are quietly wrestling with the possibility that our cosmos is less than it appears. But to appreciate what they are doing, you don't need to hold equations in your mind or visualize particles moving through 10 dimensions. All you need is curiosity, and the willingness to let go of certainty for a while. All you need is the openness to drift into the mystery as you lie here in the quiet of your own space, listening and wondering. Think of a hologram. Maybe you've seen one on a credit card or on a novelty sticker that shows a three-dimensional image when you tilt it under the light. That hologram is created by recording information on a flat, two-dimensional surface. Yet, when you look at it, you see depth. You see the illusion of three dimensions. Your eyes are convinced that something solid is there, but in reality, it is nothing more than patterns etched on a plane. The suggestion that our universe could be like this, that all of space, time, stars, and galaxies are simply the projection of information written in two dimensions, is what scientists call the holographic principle. And though it sounds like magic, it is grounded in mathematics and physics that have been tested, debated, and refined for decades. Still, it is important to remember that mystery does not mean confusion. Mystery is the doorway to wonder. Just as ancient sailors once looked at the stars and asked if Earth might be round, so too can we look at our own sky and ask if space might be an illusion. And in this asking, something happens. We feel the limits of our senses, but we also feel the limitless possibilities of thought. We begin to sense that the universe is not only vast in its size, but vast in its capacity to surprise us. And in the quiet hours of night, when the mind slows down and the world softens, this vastness becomes less intimidating and more soothing, like the gentle hum of the cosmos reminding us that we are part of a story much greater than ourselves. As you listen, you're breathing slow, your body sink deeper into rest. Imagine the three-dimensional room around you. Now imagine it dissolving into a two-dimensional pattern, like a shadow, like a painting on the surface of space. Imagine that you are both inside the picture and outside of it, both real and reflected. This is not something to solve, not something to prove tonight. It is simply something to wonder about, a mystery to hold gently in your thoughts as you drift between wakefulness and sleep. When we speak about dimensions, we are really talking about the basic framework that allows us to describe reality. A dimension is not something you can hold in your hand or put in your pocket. It is not a physical object you can measure with the ruler or capture with the camera. Instead, it is a direction of possibility, a way for movement to occur, a coordinate that helps us locate where we are and where we might go. And yet, though dimensions are abstract, they shape everything about the way we exist. They define the spaces we inhabit, the paths we travel, and even the way we imagine our place in the universe. To understand whether our world might truly be two-dimensional, or whether three dimensions are just an illusion, we first need to gently walk through what physicists mean when they talk about dimensions. The simplest place to begin is with a line. Imagine you are holding a pencil, and on a blank sheet of paper, you draw the thinnest, straightest line you can. That line, in mathematical terms, is one-dimensional. It has only one property: length. If you were a tiny creature living inside that line, you could only move in two directions, forward or backward. There would be no left or right, no up or down. Your world would stretch only along that single direction, and you would never know that other directions even existed. This is the essence of the first dimension, and though it may seem impossibly simple, it is the building block for everything else. Now imagine taking a second step. On that same piece of paper, instead of drawing another line parallel to the first, you draw a new line that crosses it. With that, a new possibility emerges, a flat plane. You now have two dimensions, length and width. In this two-dimensional world, your little line-dwelling creature has been upgraded. Now, it can move forward and backward, but also left and right. It can navigate a plane, trace shapes, create angles, and form surfaces. The two-dimensional plane is what gives us squares, circles, and triangles. It is what allows art to come alive on a flat canvas. And if we look around at things like computer screens, blueprints, and photographs, we realize how much of our daily lives still unfold in this two-dimensional way. Then comes the third leap, the one that feels most familiar to us. Add a new direction that rises out of the plane, a vertical line standing up from the flat page, and suddenly, the world blossoms into 3 dimensions. Now we have length, width, and height. The creatures of this new world can walk not just along surfaces, but through volumes. They can build cubes, spheres, pyramids. They can construct houses, skyscrapers, and airplanes. They can measure not just area, but volume, not just flatness, but fullness. This is the dimension of the body you are lying in right now, the dimension of the room around you, the dimension of the stars and galaxies you can imagine stretching above your head. It feels so natural, so deeply woven into our experience, that we rarely stop to question it. For us, the 3rd dimension is reality itself. But physics, in its endless curiosity, asks us to consider something stranger. It asks us to imagine a 4th dimension, not the 4th dimension of time, though time is often paired with space in Einstein's theory of relativity, but rather, a 4th spatial dimension, one that extends beyond length, width, and height. Just as a line dweller could not easily imagine what it means to step into a plane, and just as a flat creature in 2 dimensions might struggle to picture what it means to rise into the 3rd, so too do we struggle to picture what a 4th spatial dimension would look like. But the mathematics allows it. The equations of geometry and physics open doorways into spaces we cannot directly see, but which we can describe, model, and explore with thought. And once the 4th dimension is possible, the 5th becomes possible, and the 6th, and on and on. The world of physics is not bound by our imagination. It stretches into spaces we cannot visualize, but which still may shape the very fabric of our universe. For centuries, humans lived in a world where 3 dimensions felt sufficient. You could build cathedrals, chart oceans, map continents, and send rockets into the sky, all without needing more than 3. But as the questions grew deeper, as physicists began to ask not just how planets move, but why gravity exists, not just how atoms behave, but why quantum particles act the way they do, the mathematics began to suggest that 3 dimensions may not be enough. Certain puzzles could only be solved if you allowed for the existence of higher dimensions, hidden layers of space that we cannot touch or see, but which still ripple beneath our experience. This is where theories like string theory arise, proposing that the universe might have as many as 10 or 11 dimensions, each curled up so tightly that we never notice them, like tiny loops folded into the fabric of space itself. And yet, as mysterious as higher dimensions may sound, the possibility of fewer dimensions is equally intriguing. The holographic principle, which we will touch more deeply later, suggests that all of the 3-dimensional world we know could actually be described entirely by 2 dimensions. Imagine if the page of your notebook contained all the information to describe not just the flat shapes upon it, but an entire 3-dimensional world rising above it. Imagine if the surface of the universe itself was like that notebook page, carrying the code, the data, the instructions for every particle, every star, every thought. In such a case, what feels like 3-dimensional space may be nothing more than an emergent illusion, the way a hologram projects depth from a flat sheet. The concept of dimensions in physics is not just about counting directions. It is about understanding the language of reality. It is about asking whether what we see is the full truth, or only a shadow of something deeper. Just as Plato once imagined people in a cave, watching shadows on a wall and mistaking them for reality, we too may be living in a cave of sorts, mistaking the vivid 3-dimensional world for the deeper truth of 2-dimensional information. This thought does not diminish our world. On the contrary, it makes it richer, more wondrous, more full of mystery. Because if dimensions are not fixed, if they can shift and reveal themselves in unexpected ways, then reality itself is more flexible, more alive than we ever dared to dream. For physicists, describing dimensions is both an art and a science. They use equations, coordinates, and graphs to pin down the invisible, but they also use imagination, analogy, and metaphor to bridge the gap between mathematics and experience. They invite us, ordinary listeners, to step outside our comfort zones, to close our eyes and picture worlds we cannot see, to accept that the universe is always more than it appears. And here, in the quiet hours of night, when the mind is soft and the body is at rest, we can let those invitations sink into us. We do not need to solve the puzzles tonight. We do not need to prove the equations or test the theories. We only need to drift in the gentle realization that dimensions are the canvas of reality, and that canvas may hold secrets we are only just beginning to glimpse. There is a quiet strangeness that lingers in the background of physics, a whisper that suggests the universe is not as it seems. It begins with a simple but profound question: how much information can be stored in a region of space? At first glance, the answer feels obvious. If you think of a box, the amount of information you can fit inside it should depend on its volume. A larger box holds more than a smaller one. A three-dimensional space should be defined by three-dimensional content. But when physicists turn their attention to black holes, those mysterious regions where gravity grows so strong that not even light can escape, they began to discover that this intuition might be wrong. The information about a black hole, the way it encodes the matter that falls into it, seems to be contained not in its volume, but on its surface, on the two-dimensional boundary of its event horizon. This is the spark that led to what we now call the holographic principle. The holographic principle suggests that everything we perceive as three-dimensional reality is, in a sense, encoded on a two-dimensional surface. Just as a hologram on a credit card holds patterns that appear to rise into depth when illuminated, the universe itself may be a grand hologram, a projection of information inscribed on a cosmic boundary. This idea is not a poetic metaphor, though it carries the beauty of one. It is a mathematical proposal, developed from the union of quantum physics and gravity, and it has become one of the most influential and haunting concepts in modern theoretical physics. To lie here in the quiet, listening to this idea unfold, is to step into a dream where walls dissolve, where depth becomes an illusion, and where the very stage on which life plays out may be thinner and stranger than we ever imagined. To appreciate the holographic principle, it helps to pause and think about holograms themselves. A hologram is not a simple picture. It is created by capturing the interference of light waves, recording not just the brightness, but also the phase information of light. When you shine a light on a hologram, the image you see appears three-dimensional, yet it is generated from data stored on a flat surface. Your eyes and brain are convinced there is depth, but the depth is only an emergent effect. The real information lives on the plane. In a similar way, the holographic principle suggests that the depth of our universe, the galaxies spread across space, the atoms vibrating in your body, the immense expanse we call three-dimensional reality, might be nothing more than an emergent effect, the projection of information encoded on a distant surface we cannot see directly. This surface, in theoretical physics, is often imagined as the boundary of the universe itself, a kind of cosmic horizon that holds the information of everything inside. Just as a black hole's event horizon encodes the information of its interior, so too could the universe's horizon encode the information of everything within. When you reach out and touch the table beside you, when you breathe and feel your chest rise and fall, you are participating in the projection of that hidden information. You are a hologram, a three-dimensional emergence from a two-dimensional script written on the fabric of the cosmos. The idea sounds radical, but it grows from necessity. In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking discovered that black holes have entropy, a measure of disorder or information. To everyone's surprise, the entropy of a black hole was not proportional to its volume, but to the area of its surface. The information was written on the skin, not stored in the core. This was more than a curiosity. It hinted at a new principle of nature, one that could resolve paradoxes between gravity and quantum mechanics. The holographic principle rose from these hints, becoming a lighthouse in the fog of theoretical physics, guiding researchers toward a new way of thinking about reality. In the 1990s, physicist Juan Maldacena provided one of the most powerful formulations of this principle, showing that in certain models of the universe, a theory of gravity in three dimensions is mathematically equivalent to a quantum field theory on a two-dimensional boundary. This was not just philosophy, but a precise, testable duality. It meant that two descriptions of the universe, one in a world with gravity and depth, the other on a flat surface without gravity, were in fact the same. Two languages, one reality. Two perspectives, one truth. The implications of this are still being explored today, but they ripple outward in every direction, raising questions about whether our own universe, with its galaxies and planets and life, might be fundamentally holographic. To imagine this in a way that feels tangible. Picture a snow globe. Inside the globe, you see a little world. Houses, trees, maybe a tiny person walking along a snowy street. To you, looking in from the outside, that scene has depth. But now imagine that every detail of the snow globe is actually stored on the surface of its glass. The houses, the trees, the tiny figure, they are all projections, coded into patterns on the glass itself. This is how the holographic principle asks us to reimagine the universe. Everything you see inside, the stars above, the earth below, your own heartbeat, is not the full story. The story is written on a surface, and the depth you perceive is a grand projection. For many listeners, this can feel unsettling. If the world is a hologram, does that mean it is not real? Does it mean our lives are illusions, like shadows in Plato's cave? But physicists are careful here. A hologram is not unreal. The three-dimensional image is not fake. It is a real effect of real information. The world you touch and see is genuine. What changes is not the reality itself, but the way reality is structured beneath the surface. The holographic principle does not erase the universe, it deepens it, suggesting that beneath the layers of space and time lies a foundation of encoded information, an elegant order from which everything emerges. And there is something deeply comforting in that. It suggests that nothing is lost, that the universe keeps track of every detail, every event, every particle, not in the depths of space, but on the surfaces that surround it. It suggests that you, too, are part of this grand code, woven into the cosmic script. And as you drift here, listening, you might feel a quiet wonder at the possibility that your life, your story, your very being, is written into the fabric of the universe itself, preserved on its surface, projected into the depth you experience. Black holes are among the most mysterious and fascinating objects in the universe. They are regions where gravity grows so intense that not even light can escape. To most of us, they feel like cosmic monsters, devouring everything that comes too close. We imagine them as bottomless pits in space, endless wells of darkness, swallowing stars and planets with a hunger that cannot be satisfied. Yet for physicists, black holes are not simply places of destruction. They are also laboratories, testing grounds where the deepest laws of the universe reveal themselves. And it is in the study of black holes that the strange idea of a two-dimensional universe first gained real traction. To understand why, imagine you are floating near the edge of a black hole. You would be near the event horizon, the boundary beyond which nothing can return. Cross that invisible threshold, and you are gone from the universe's point of view, swallowed into the singularity at the black hole's heart. To you, falling in, the passage may feel smooth, but to outside observer, you would appear frozen in time at the event horizon, your image smeared and stretched, your information trapped on the surface of the black hole. That word information carries great weight. In physics, information means the details about the matter and energy that make up reality. The spin of particles, their positions, their interactions, the patterns that define them. And what scientists discovered, to their amazement, was that the information about everything falling into a black hole was not lost inside its volume. Instead, it appeared to be recorded somehow on the two-dimensional surface of its horizon. This idea was revolutionary. For centuries, science assumed that information about an object was contained within the object itself, spread out through its volume. A sphere of water holds its properties throughout its liquid. A stone holds its details in every particle that makes up its mass. But a black hole defies this intuition. It is as if the entire identity of everything that has ever fallen into it is etched on its outer skin, the way words are etched onto a page. A black hole is not so much a three-dimensional container, but a two-dimensional archive. The boundary holds the secrets, the surface remembers the past, and the depth is not what it seems. Stephen Hawking brought this mystery into the public eye when he showed that black holes are not completely black. They emit radiation, a faint glow now known as Hawking radiation. This revelation led to a paradox. If black holes radiate, then over time, they shrink and eventually vanish. But if they vanish, what happens to the information about everything they once swallowed? In the laws of physics, information is supposed to be conserved. It cannot simply disappear. Yet if the contents of a black hole evaporated into nothingness, it seemed that information might be lost forever. This puzzle became known as the black hole information paradox, and it has haunted physics for decades. One of the most promising answers to this paradox is that the information is never really lost. Instead, it is preserved on the event horizon, in two dimensions. Think of it like a cosmic storage device, a surface that records the details of everything within. If this is true for black holes, then perhaps it is true for the universe itself. Perhaps the three-dimensional space we see all around us is really just the projection of two-dimensional information, just as the depth of a hologram is a projection of data written on a flat sheet. Black holes, in this sense, are not only astrophysical curiosities, they are windows into the deepest architecture of reality, showing us that the universe might be a hologram, and that everything we experience in three dimensions is ultimately written on a two-dimensional boundary. To picture this, imagine once more a snow globe, filled with swirling flakes. The globe looks rich and full, with layers of depth. But now imagine that everything inside the globe is actually described on its outer glass. The flakes, the houses, the tiny figures, all of them are projections, illusions of volume created from patterns on the surface. A black hole, too, may work this way. The vast three-dimensional interior may be nothing but a projection, with the real information resting on the thin, two-dimensional shell of its horizon. What falls in does not vanish into an unreachable core. It leaves its signature on the boundary, etched into the cosmic skin. For many physicists, this realization was both unsettling and inspiring. It overturned long-standing assumptions about how space and matter should behave. But it also opened a door to new theories, new ways of reconciling gravity with the strange laws of quantum mechanics. In the United States, scientists working at places like Princeton, MIT, and Stanford have devoted years to exploring these puzzles. Using mathematics as their telescope, they peer into the structure of black holes, uncovering relationships between gravity, quantum fields, and information. They are not only seeking to understand black holes themselves, but also hoping to uncover the principles that govern the entire universe. If black holes are holograms, then perhaps the universe is too. One of the remarkable things about black holes is how they force us to rethink the very nature of reality. If all the information about a star, about a planet, or even about a person could be encoded on a surface, then depth itself may be an emergent property. The space inside may not be fundamental. Instead, it may arise from the interplay of information stored on the boundary. This is a radical shift in perspective, but it is one that fits neatly with the holographic principle. It suggests that our universe, rich in volume, teeming with galaxies and nebulae, may be more like a vast black hole in its own right, its secrets stored on the edges, its depth a grand projection. As you lie here and let your mind wander, you might imagine yourself drifting at the edge of a black hole. You might picture the event horizon not as a frightening boundary, but as a cosmic canvas glowing faintly, carrying the encoded story of everything that has ever passed through. You might picture information itself flowing across that surface, like ripples of light, like delicate etchings in an infinite script. And then you might extend that vision outward, imagining the universe itself as a great horizon, with all of reality written upon it. The stars, the planets, the people you love, the moments you remember, they are all part of that vast two-dimensional code, projected into the depth you experience. The quest to understand the universe often begins with simple questions. What is matter made of? How does gravity work? Why do particles behave the way they do? For centuries, science has chipped away at these questions, peeling back layers of mystery. First atoms, then electrons and protons, then quarks hidden inside. Protons. Each discovery felt like reaching bedrock, only to find another layer beneath. By the late 20th century, physicists were confronted with two great pillars of knowledge that seemed impossible to unify: Einstein's theory of general relativity, which explains gravity and the large-scale structure of the universe, and quantum mechanics, which explains the strange behavior of particles on the smallest scales. Both theories worked beautifully in their own domains, but when applied together, they clashed. Somewhere, hidden in the mathematics, the universe was hinting at a deeper theory that could embrace both. Out of this tension, string theory was born. String theory proposes that the most fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings are unimaginably small, so small that if an atom were the size of the Earth, a string would be the size of a tree on that Earth. They vibrate in different ways, and their vibrations give rise to the particles we know. An electron is not a tiny dot, but a string vibrating in one pattern. A photon, the particle of light, is a string vibrating in another. The richness of the universe, the diversity of matter and energy emerges from the symphony of these strings, each playing its own note in the cosmic orchestra. The beauty of string theory lies not only in its elegance, but also in its necessity. When physicists tried to calculate certain aspects of quantum gravity using traditional particle theories, the results often diverged into infinities, numbers so nonsensical they threatened the very foundations of science. But when the calculations were done with strings instead of points, those infinities melted away. The equations suddenly made sense. The universe seemed to whisper that perhaps strings, not particles, were its true building blocks. But there is a price. For string theory to work, it requires dimensions beyond the three we know. Instead of length, width, and height alone, the strings need extra directions in which to vibrate. Depending on the version of the theory, the universe must have 10 or 11 dimensions. Some of these dimensions, physicists propose, are curled up so tightly that we cannot see them, compactified into loops smaller than any microscope could ever detect. Imagine rolling a sheet of paper into a tiny tube. From far away, it looks like a one-dimensional line, but up close, you see its two-dimensional surface. In the same way, dimensions beyond the familiar three might be hidden, wrapped so closely that they escape our perception. This idea is not just mathematical play. It is one of the few ways physics has found to reconcile gravity with the laws of quantum mechanics. And within string theory lies a remarkable connection to the holographic principle. In the 1990s, physicist Juan Maldacena showed that a type of string theory describing gravity in a curved three-dimensional space is equivalent to a quantum field theory without gravity on a two-dimensional boundary of that space. This duality, known as ADS or CF correspondence, is perhaps the most concrete realization of the holographic principle. It means that two very different theories, one with gravity in 3 dimensions, and one without gravity in 2, can describe the same reality. It is as if the universe has 2 faces, one deep, curved, and full of gravity, the other flat, abstract, and gravity-free. Both are valid, both are real, and both are connected by a bridge of mathematics. This duality suggests that our own universe may work in much the same way. It strengthens the possibility that our 3-dimensional world could be the projection of a 2-dimensional reality, that depth itself may be a kind of illusion. In this view, string theory does more than unify gravity and quantum mechanics. It also hints that the universe is fundamentally holographic, its richness encoded on a lower dimensional surface. It is as if the universe has written its story in 2 dimensions, and we live within the unfolding projection. Of course, string theory is still a theory. It has not yet been proven by experiment. The strings are too small to detect directly, and the extra dimensions, if they exist, are too tightly curled to observe. But the mathematics continues to inspire. offering pathways into mysteries once thought unreachable. In universities and research institutes across the United States, physicists spend long nights exploring these pathways. They imagine how extra dimensions might shape the particles we see in accelerators. They wonder if the ripples of gravity detected by observatories like LIGO might carry whispers of hidden strings. They build bridges between quantum information theory and cosmology, uncovering deep patterns that echo through both black holes and entangled particles. The phrase, "and beyond," matters here, because string theory, as powerful as it is, may be just one step along the road. Some physicists speak of M-theory, an even broader framework that includes string theory as one of its many possible faces. Others explore loop quantum gravity, a rival approach that tries to weave spacetime itself into tiny loops, like a vast fabric. Still, others are drawn to emergent gravity, where spacetime is not fundamental but arises from the entanglement of quantum information, like warmth arising from the motion of molecules. These approaches may seem different, but they share a common spirit: the recognition that the universe is more subtle, more layered, more wondrous than our everyday senses suggest. In many ways, string theory and its cousins are like dreamscapes. In physics, they invite us to imagine a world where the dimensions we walk through are not fixed, where depth and time are malleable, where reality is written in vibrations, loops, and codes. They ask us to hold two truths at once: that the universe is here, solid and tangible, and that it is also something stranger, deeper, and more abstract than we can easily picture. They remind us that physics is not only about measuring and calculating, it is also about wonder, about daring to imagine what lies beyond the visible horizon. As you listen and drift, you might picture the strings themselves, tiny, delicate threads of energy, vibrating softly in the silence of space. Some quiver gently, others hum with intensity, together forming the grand symphony of existence. You might picture extra dimensions curling tightly around them, invisible yet real, like secret passageways in the fabric of reality. You might imagine the entire universe as a kind of instrument, each vibration weaving the stars, the planets, the light of the galaxies, the breath you take. And then, you might feel a quiet awe at the thought that even in the vastness of space, you are part of that song, a note in the endless melody of strings. When scientists propose daring ideas about the universe, they are not content to leave them in the realm of theory. They want evidence. They want experiments, observations, and data that either confirm or challenge their imagination. The notion that our universe could be two-dimensional, projected as a hologram into the three-dimensional world we perceive, is bold. It challenges centuries of intuition, centuries of lived experience. And yet, in quiet laboratories and vast observatories, researchers are searching for signs, for traces of this hidden truth. They look to the sky, to the cosmic background of the universe, to the delicate whispers of quantum noise, all to see if the holographic principle is written into the fabric of reality itself. One of the most compelling places to look for evidence lies in the afterglow of the Big Bang. More than 13 billion years ago, the universe burst into being, expanding from a state of incomprehensible density and heat. As it expanded, it cooled, and light was finally able to travel freely. That light, stretched into microwaves by billions of years of cosmic expansion, still fills the universe today. It is known as the cosmic microwave background, a faint, ancient glow that astronomers can detect with radio telescopes. To scientists, this background is like a photograph of the infant universe, a snapshot taken just 380,000 years after the Big Bang. And hidden within the tiny fluctuations of that light, there may be clues to the dimensional structure of reality itself. If the universe is holographic, then those fluctuations in the cosmic microwave background might show patterns that reveal it. The noise in the data, the statistical fingerprints of the early universe, could carry signs that space is not as continuous or smooth as it appears, but instead emerges from a two-dimensional foundation. In the United States, projects like NASA's Wilkinson microwave anisotropy probe, and later the Planck satellite launched by the European Space Agency, have mapped the cosmic background in extraordinary detail. With each new map, scientists search for subtle deviations, hints of holographic behavior. Some researchers have even claimed that certain anomalies in the data could be interpreted this way, though the evidence remains tentative. The conclusion still debated. Another place to search for holographic evidence lies not in the sky, but in carefully controlled experiments here on Earth. At Fermilab in Illinois, scientists developed an experiment called the holometer. Its goal was audacious: to test whether the fabric of space itself is holographic. The holometer used powerful lasers split into beams that traveled down long, perpendicular tunnels. By comparing the interference patterns of the beams, the experiment aimed to detect tiny jitters in space, fluctuations that might arise if space is not continuous but pixelated, like an image projected from a two-dimensional source. The idea was that if our universe is holographic, space would not be infinitely smooth. Instead, it would have a graininess at the smallest scales, a kind of quantum fuzz that betrays its two-dimensional origins. The holometer operated for several years, collecting data, searching for this subtle noise in reality. Its results were not conclusive, but they opened a path forward. They showed that even the wildest ideas in theoretical physics could be approached with experimental ingenuity. They reminded us that the universe is not beyond our reach. Even questions as abstract as, is the universe two-dimensional, can, in principle, be tested. And in that pursuit, there is a beauty, blending of imagination with precision, of wonder with rigor. Gravitational waves offer another window into the question. These ripples in spacetime, predicted by Einstein a century ago, and first detected in 2015 by the LIGO observatories in the United States, are created when massive objects like black holes or neutron stars collide. They travel across the cosmos, stretching and squeezing space as they go. Some physicists have speculated that if the universe is holographic, then gravitational waves might carry subtle distortions, signatures of the underlying two-dimensional structure. Observatories like LIGO and Virgo are now sensitive enough to measure changes in length smaller than a fraction of a proton. With each new detection, they not only confirm Einstein's theory, but also provide fresh data to test deeper, holographic models of the universe. Cosmic rays, too, have been proposed as messengers. These are high-energy particles that rain down on Earth from space, sometimes carrying more energy than the most powerful accelerators humans have ever built. They crash into the atmosphere, producing showers of secondary particles that scientists capture with detectors spread across deserts or embedded in ice. Some researchers suggest that the way these cosmic rays scatter and distribute might reveal hints of holography. If the underlying structure of space is two-dimensional, then the highest energy particles might behave differently than expected, deviating from three-dimensional predictions. Each of these approaches cosmic microwave background analysis, the holometer, gravitational wave observatories, cosmic ray detectors represents humanity's attempt to pull on the threads of reality and see what unravels. None have yet provided a definitive answer. The holographic principle remains a powerful idea supported by mathematics, but not yet confirmed by observation. And yet, the pursuit itself is remarkable. It shows that science is not static, not bound by what seems obvious. It is willing to question even the most fundamental assumptions, to test whether the stage on which reality unfolds is truly three-dimensional, or whether that stage is a projection from something deeper and simpler. Beyond specific experiments, there is also the role of quantum information. Increasingly, physicists are discovering that the language of information may be the most fundamental language of all. Black holes, as we have seen, encode information on their surfaces. Quantum entanglement, where particles separated by vast distances share instantaneous connections, seems to stitch space together like invisible threads. Some researchers propose that spacetime itself might be an emergent phenomenon, arising from the entanglement of quantum information, much as temperature emerges from the collective motion of molecules. If this is true, then the holographic principle is not just a strange possibility, it is a natural consequence of the way information builds reality. In the United States, at universities from Caltech to MIT, at national laboratories like Fermilab and Brookhaven, and in observatories spread across deserts and mountaintops, scientists are piecing together this puzzle. They are combining data from the heavens with theories born in chalk-filled lecture halls. They are running simulations, building detectors, designing experiments that stretch human ingenuity. And though the evidence is still forming, each attempt draws us closer to understanding whether the three-dimensional world we trust is as fundamental as it feels, or whether it is a grand projection, a hologram written on the edges of the cosmos. As you rest and listen, you might imagine these experiments as quiet acts of curiosity, like lanterns glowing in the dark. Each laser beam in the holometer, each ripple of a gravitational wave, each pixel of the cosmic microwave background is a lantern, illuminating a piece of the mystery. Together, they form a constellation of inquiry, a pattern of human wonder stretching across space and time. You might picture the scientists themselves, not as distant figures in lab coats, but as fellow travelers, lying under the same stars, asking the same questions that echo in your own mind. And you might let that thought carry you gently into the vastness, into the wonder of a universe that invites us to search for its secrets, even as it cradles us in the quiet of the night. When we consider the possibility that the universe is not truly three-dimensional, but instead a projection from a two-dimensional reality, the question moves beyond physics. It enters the realm of philosophy, where science and meaning entwine. To imagine that everything we see, touch, and experience could be the shadow of a deeper reality is to confront the very foundations of human thought. For thousands of years, philosophers have asked what is real, how we can know it, and whether the world as it appears is the world as it is. The holographic principle does not just add a new scientific theory to the mix, it breathes new life into these age-old questions, suggesting that perhaps reality itself is stranger and more subtle than anyone imagined. The first philosophical implication is about perception. We trust our senses to guide us. The solidity of the ground beneath our feet, the depth of the sky above, the distance of a horizon, all of it feels unquestionably real. Yet science has already shown us that our senses are limited. The colors we see are only a small portion of the electromagnetic spectrum. The sounds we hear are just a narrow range of vibrations. The textures we touch are interpreted by nerves and translated by the brain. If the holographic principle is true, then even the space we perceive, height, width, and depth, is a kind of construction, an interpretation of data. This would mean that reality as we experience it is not the universe in its true form, but a translation, a projection filtered through the architecture of space itself. It would mean that our everyday perception is, in some sense, a useful illusion. This thought echoes the ideas of philosophers stretching back to antiquity. Plato, in his allegory of the cave, described humans as prisoners watching shadows on a wall, mistaking those shadows for reality. For him, the true world lay beyond the cave, a higher realm of forms and ideas. The holographic universe is not the same as Plato's cave, but the resonance is uncanny. We, too, might be living among shadows, our three-dimensional world a projection of a two-dimensional truth. What feels solid may be no more substantial than the patterns of light and shadow cast upon the walls of the cosmos. Another implication arises when we consider identity. If reality is a projection, what does that mean for the self? We think of ourselves as embodied beings moving through space, our bodies occupying volume, our minds housed within our brains. But if space itself is an emergent illusion, then identity may not be tied so firmly to physical extension. It might be something encoded in the deeper layers of the universe, in the informational structures that give rise to projection. This does not diminish our humanity. Rather, it suggests that who we are is woven into the fabric of reality at a more fundamental level than flesh and bone. It opens the door to imagining consciousness not as a byproduct of matter, but as part of the foundational code of the cosmos. There is also the question of meaning. For centuries, many have looked to the stars and felt small, overwhelmed by the vastness of a three-dimensional universe filled with galaxies upon galaxies. But if the universe is holographic, then perhaps vastness itself is not what it seems. Perhaps the endless depth we imagine is an unfolding of information written on a two-dimensional surface. If so, then our place in the universe is not defined by how small we are compared to physical distances, but by how deeply we are embedded in the cosmic code. Meaning, in this sense, may not come from our physical scale, but from our participation in the story the universe tells of itself. The holographic principle also raises questions about free will and determinism. If reality is information encoded on a boundary, then in some sense, the entire universe could be seen as a vast computation, unfolding according to rules inscribed at the edge. Are our choices real, or are they part of the unfolding pattern? Do we have freedom, or are we playing out lines already written in the holographic script? Philosophers and scientists alike wrestle with this, though many remind us that even if reality is encoded, unpredictability is built into the fabric of quantum mechanics. The future may be open, not predetermined, even if it arises from a deeper order. The paradox is that we may be both characters in a story and authors of our own chapters, the projection and the projector intertwined. The idea of a holographic universe also invites reflections on spirituality. Throughout history, cultures have imagined that the world we see is not the ultimate reality. Mystics speak of hidden dimensions, unseen planes of existence, and deeper truths veiled from ordinary perception. While science and spirituality are distinct, it is striking how the holographic principle resonates with these ancient intuitions. To think of the universe as projection is to acknowledge that what we see may not be the whole story. For some, this provides comfort, a sense that the visible world is part of something greater. For others, it provides a reminder that mystery is not banished by knowledge but deepened by it. The principle also forces us to think differently about death and continuity. If reality is projection, then what happens to us when the projection changes? Are we erased, or do we persist in the underlying code? In some interpretations, the information that defines us cannot be destroyed. It is conserved, woven into the fabric of the hologram even if our three-dimensional form dissolves. This is not an answer to the mystery of death, but it offers a new way of contemplating continuity, of imagining that perhaps our existence is not so fragile as it seems. At a broader level, the holographic principle challenges human hubris. It reminds us that the way reality feels to us is not necessarily the way reality is. Just as the Earth once seemed flat until exploration and observation revealed its curvature, and just as the heavens once seemed to revolve around us until science revealed otherwise, so too our three-dimensional perception may be provincial, a local truth within a larger picture. The universe, in this view, is always more than we expect. It humbles us, even as it invites us to imagine more deeply. In the United States, where philosophy and science often meet in classrooms, universities, and public dialogue, these questions resonate strongly. The American tradition of pragmatism, born in the 19th century, asked how ideas matter to lived experience. If the universe is holographic, how does that change the way we live? Perhaps it calls us to humility, to recognize that our place in the cosmos is not to dominate or control, but to participate in a grand unfolding we can scarcely comprehend. As you listen, you might imagine yourself standing beneath a star-filled sky. You see the depth, the endless black sprinkled with light. You feel the weight of that immensity, and then you imagine that all of it, the stars, the galaxies, the depth of space, is a projection. The true reality lies on an invisible surface, beyond what your eyes can see. You are both inside the projection and part of the surface that encodes it. You are both shadow and substance. You are both finite and infinite. You are both question and answer, folded together in the holographic mystery of being. To imagine that we might be living in a holographic universe is to stretch the boundaries of thought itself. It asks us to take an abstract mathematical principle, born in the minds of physicists, and apply it to the rhythm of our everyday lives. The holographic principle does not remain locked in blackboards and equations. It invites us to consider how we walk through the world, how we see ourselves, how we make sense of existence. It challenges the way we define reality, and it asks what it means to live meaningfully in a universe where depth may be an illusion and solidity may be a projection. First, this thought can feel unsettling. We live by trusting our senses. We look at a mountain, and we feel its immovable presence. We reach for a glass of water, and we trust the space between our hand and the glass to be real. To learn that what we see as three-dimensional depth may, in fact, be encoded on a two-dimensional boundary, is to wonder whether everything familiar might be less certain than it seems. And yet, if we look more closely, we realize that we have always lived with layers of illusion. We already know that color is not an inherent property of objects, but the brain's interpretation of light frequencies. We know that time does not flow uniformly, that it bends and stretches depending on speed and gravity. The holographic principle is another step in this unfolding awareness, another reminder that reality is richer and more complex than our senses suggest. Living in a holographic universe means living with humility. It means accepting that what feels obvious may not be ultimate. It means remembering that reality does not owe us simplicity or comfort. Instead, it challenges us to expand, to let go of certainty and embrace wonder. For many in the United States, where science and technology shape daily life in profound ways, this humility is especially resonant. We live in a society where answers are prized, where clarity is expected, and yet science itself tells us that the deepest truths are often counterintuitive. To embrace the holographic universe is to learn to rest in paradox, to be comfortable with mystery, to see the unknown, not as a void, but as an invitation. There is also a practical side to this. If reality is a projection of information, then information becomes central to everything. Every interaction, every thought, every particle is not just a physical thing, but also a bit of encoded data woven into the cosmic fabric. Living in such a universe, we might begin to see ourselves less as isolated individuals and more as nodes in a vast informational network. Just as pixels on a screen combine to create an image, so too do our lives combine to create the living projection of the cosmos. This perspective can change the way we treat one another. It suggests that we are deeply interconnected, not just socially or biologically, but at the most fundamental level of reality. To harm another is not simply to harm someone else, it is to disrupt the harmony of the projection we all share. To act with kindness is to bring coherence to the hologram, to align ourselves with the deeper order of things. Some may ask whether living in a holographic universe diminishes meaning. If we are shadows of a deeper truth, does that make our lives less real? But the opposite is also possible. Shadows can carry beauty, projections can carry depth. A hologram is not an absence of reality, it is a different expression of it. In the shimmering layers of a holographic image, every piece contains the whole. In the same way, our lives may carry the fullness of the universe within them, even if they are part of a projection. To live in a holographic universe is not to live in unreality. It is to live in a reality that is layered, encoded, and endlessly subtle. This way of thinking also resonates with creativity and imagination. Artists, writers, musicians all work with projections, with representations of reality. A painting is not the thing it depicts, yet it carries meaning. A song is not the experience it describes, yet it evokes feeling. To live holographically is to live artistically, to recognize that representation does not erase significance. It may even enhance it. Just as art can open us to truths deeper than literal description, the holographic universe may open us to truths deeper than physical appearance. Living with this awareness can make life itself feel like art, a projection filled with meaning, shaped by hidden dimensions of truth. The holographic principle also influences how we think about technology. In the United States, we are surrounded by digital projections, by screens that create images from flat surfaces. Virtual reality, augmented reality, holographic displays, all of these technologies give us experiences of depth that are not literally there. The holographic universe is not a digital simulation, but the parallels are striking. Just as pixels and codes can generate immersive worlds, so too might the cosmic code generate the world we inhabit. To live with this thought is to blur the boundaries between technology and nature, to see both as expressions of information unfolding into experience. It may change the way we approach innovation, reminding us that technology is not alien to reality, but echoes the same informational patterns woven into the cosmos itself. And then there is the question of mortality. If we are part of a holographic projection, what happens when the projection shifts, when our individual presence dissolves? Some physicists suggest that information in the universe is never lost, that it is always preserved at the most fundamental level. If so, then living in a holographic universe might mean that who we are, the information that defines us, remains encoded, even if our three-dimensional form fades. This does not resolve the mystery of death, but it reframes it. It suggests continuity, the possibility that nothing is ever truly erased. For some, this is a comforting thought. For others, it is a reminder of responsibility, that our actions and choices are woven into the code of reality itself, leaving imprints that endure. Living in a holographic universe also affects how we think about the future. If the cosmos is written in code, then the unfolding of that code is not fixed, but full of potential. Just as a holographic image can shift depending on how light strikes it, so too might reality shift depending on how information unfolds. The future may not be predetermined, but emergent, arising from the interplay of countless informational threads. To live with this awareness is to live with openness, to see the future not as a rigid path, but as a hologram still being illuminated. It invites us to act with creativity, to bring intention into the projection, to shape the way the cosmic image unfolds. Perhaps most importantly, living in a holographic universe deepens our sense of wonder. It reminds us that beneath the surface of the familiar lies an infinity of mystery. The ground we walk on may be a projection, but it carries the weight of stars. The air we breathe may be woven from hidden dimensions, but it sustains life with every inhale. Every moment becomes richer when we see it as part of a cosmic hologram, encoded and projected from a place beyond sight. Wonder then becomes not a passing emotion, but a way of being, a steady awareness that reality is never exhausted by what it appears to be. As you listen, you might imagine yourself not as a small figure in an endless three-dimensional void, but as a luminous strand of information shimmering within the projection. You might picture the universe as a great hologram, its surface inscribed with the codes of existence, projecting the galaxies, the planets, the light of the stars, and the story of your life. You might let that vision surround you like a gentle fabric, comforting in its strangeness, calming in its depth. And you might allow yourself to feel, for just a moment, that to live in a holographic universe is to live in a reality that is both more fragile and more magnificent than it seems. A reality that invites you not only to observe, but to belong, to shine, to be. We have traveled far together, from the first whisper of a question whether the universe is truly three-dimensional or only a projection, through the winding paths of physics, philosophy, and imagination. Along the way, we have paused to consider the fabric of spacetime, the paradox of black holes, the boldness of the holographic principle, the elegance of string theory, and the experiments that seek to test these daring ideas. We have asked not only what the universe is made of, but what it means to live within it, and how it shapes the stories we tell about ourselves. The possibility of a holographic universe reminds us that reality is not always what it seems. Depth may be illusion, space may be emergent, and the solidity we rely on may be a projection of something simpler and stranger. Yet, in that strangeness there is no loss of meaning, only the deepening of wonder.